Well, thank you very much for the invitation. I'm very happy to be here today. And I'm going to be talking about one of the topics that I love like the most probably, which is end-to-end driving or using artificial intelligence and machine learning to create autonomous solutions in the space of automotive or really any other space. But primarily today, I'm going to be talking about automotive and how we can leverage CARLA for that. So I made a mistake. I prepared the presentation thinking that this was like 40 minutes, and I know this is like 30 minutes, so I'm gonna need to improvise a little bit. Okay. Bear with me. So, okay, why end to end? What are you trying to solve here? So the world is a very complex place, right? There are situations that are very hard to handle or anticipate. So when you try to go the traditional way with modular approaches and divide and conquer, and you have your perception stack, your planner, etc. Well, first of all, your perception stack needs to deal with some of these measures. And if it doesn't get it right, there's no chance that your planner can do anything really to solve the problem. So you have failed already in stage one, perception. Humans can intuitively solve these kind of situations in a safe fashion, right? Like if you are encountered with a super huge mega traffic light that has like 20, well, you're gonna find a way to proceed safely without killing anyone, most likely, right? Even if you don't fully understand which traffic light is controlling which lane, etc., you're gonna find a way, right? You have some level of common sense, reasoning, intuition in the driving problem. Basically, end-to-end attempts to kind of like build the same set of intuitions without having to depend too much on particular modules producing the right output for everything to work together in harmony. So I think many of you are probably familiar with the classical directional approach to robotics and to autonomous driving as being a field of robotics. So basically divide and conquer. So, we start with sensors, we put together a perception stack, solving many scene understanding problems, including localization, object detection, etc. So hopefully the output of that perception stack is good enough so that your planner can take that high-level representation and come up with a good global plan and a local plan. Basically, that plan will be transformed into a control signal for longitudinal control, lateral control, control of all your blinkers, etc. Hopefully your controller should be able to do a good job with information that the planner provided. And finally, all that information coming from the controller will go to your actuation system, and the machine will do its thing. Now, if something goes wrong in any of these stages, chances are that you are gonna crash or you're gonna do a traffic infraction, etc. This is the traditional paradigm. And you need teams expert in each of these areas to get the problem solved. So it's complicated. It's complicated. Like you need more resources, you need people that are specialized in the different areas. You don't know sometimes where the problem is coming from. Do you need to keep working on your perception stack? Do you need to make your planner better? It's complicated, right? Now, move on to an end-to-end paradigm, which is basically what you have on the screen right now. You have sensors, and then you have an agent that in this case is basically a neural network or a combination of many neural networks, which has one mission: to drive. Right? It's one problem. Data comes in, actuation comes out. So you can have the same amount of people that you had before, all focused on this one problem. So we're turning a very complex multidisciplinary engineering problem into a problem that data scientists and machine learning engineers can tackle. More data comes in, the better your model gets. That's great. That's the dream of any AI researcher and engineer, right? There has been an evolution in end-to-end driving. And if you're interested to learn more about this evolution, I recommend you to scan this QR code because I have created a curated list of papers showing how things evolve. I'm going to be talking a little bit about it in a few minutes, but we're not where we are today like overnight. Like a lot of things happen, and I'm going to be talking about those things. So I created this diagram, sort of replicating a little bit some of the diagrams that are typically used in business. Probably you are all familiar with the Gardner curve of excitement and disappointment, etc. So something like that happened for end-to-end driving. So end-to-end driving actually started long time ago, in the 80s. And in the 80s, when artificial intelligence was still, going through their first winters, someone decided that maybe they could drive using neural networks. And they did a good job. And there was a peak of excitement in the academic world, and then it faded out and died for many years. And then in the 2000s, we have another peak in academia. So some people thought like, hey, we should resurrect this, the technology has improved, we should try again. Another peak of excitement in academia, and then it faded out. Then in 2016, members of the previous team, now at a different place at NVIDIA, say, hey, maybe we should try this again. We have GPUs that are amazing. We have a lot of data. We have something called deep learning these days. Maybe we should give it a try. A lot of excitement. Now it actually reached excitement. They propagated this from academia to industry. Industry was a little bit excited about it, but still industry thought, well, it's still kind of like a toy. I mean, academics are playing with it, but this is not going to land anywhere in production. And eventually, the time went by. We moved into the 2020s. Then we have companies like Tesla and Wave and Li Auto saying, actually, end-to-end driving kind of works. And it let us focus our resources in just the problem of driving. So, and that created a wave, not just in industry, but in the market. VCs started caring about this and say, hey, maybe end-to-end driving is something that is worth funding. And companies like Wave receive billions of dollars in funding. So, it has been a slow evolution. These are the guys that probably popularize end-to-end in the market world these days. So this is Wave, is a UK company, has received a lot of attention recently. The video, the clip that you are watching is basically an autonomous vehicle in London, driving in London, fully end-to-end using a camera-only technology, right? And it does a pretty good job. Now, but let's see, how did all of this start? Let's take a look, because I think it's very interesting. So as a quick reminder, and if you are not very familiar with this concept, so basically, as I explained before, the whole idea is that we don't want to divide this into many sub-problems, because that makes things complicated. We're going to have a neural network, an agent, and the agent is going to be in charge of controlling a set of actuators from some inputs, and these inputs typically are going to be like camera feed, lidar feed, whatever sensors you want. And typically we're going to collect, there are many ways to train these systems, but traditionally we're going to collect expert data. So experts are going to be demonstrating what's the right way to handle different situations. Basically using those supervision signals, we're just going to train this model. That's one of the traditional approaches. Now, you might be surprised to know that one of the first attempts to end-to-end driving happened in the 80s, way before deep learning was invented, right? So the Alvin project by CMU actually put together a system, like a real-world system, that was able to kind of like follow a lane, right? And we're talking about the 80s. They use synthetic images. That's something also very impressive. Like they know this, like, look, we are not able to do this with real world images per se, because it's kind of risky to acquire this data. We don't have good mechanisms to acquire this data. Why don't we synthesize low resolution synthetic images and try to train neural networks, very compact neural networks, to drive using these images? And it worked. And they created like around 1,000 of these synthetic images in different configurations. They trained a small neural network using backpropagation, it works. And they were able to drive a real-sized vehicle around the CMU campus for 400 meters. It's not a lot, but by the time, it's a significant achievement. So this was one of the first, end-to-end solutions in the world. Then move forward to 2004. There was a guy who seems to like neural networks a lot. His name is Jean LeCun, right? He's the inventors of CNNs and one of the godfathers of deep learning. And he was at New York University, and he decided to attack the problem again. So in this case, they have a small RC vehicle, and they have technology have already improved quite a lot, so that actually they could do this in real time with very simple hardware. And they decided to train like relatively deep neural networks. And again, this is before deep learning, the deep learning term was coined. This is 2004, way before AlexNet. But John LeCun used CNNs in this context to train a model that was able to drive using just camera feed, 2 cameras put in the front of a small vehicle. It was trying just to navigate around, avoiding obstacles, and it was able to perform on device at around 15 frames per second, 50 hertz. It's really impressive for 2004. So things were getting better. So it was able to steer automatically, avoiding obstacle. Great work. Then, of course, as I mentioned before, the idea died again. People didn't care too much. And then 2016, some of the team that created Dave moved to NVIDIA and decided to attack the problem again with newer technologies. And after deep learning had been invented, to do this at the scale in the real world. So basically, they took a lot of images around New Jersey and started training convolutional neural networks to solve the problem. I had the pleasure to actually visit them at the time in 2016, go there and talk to them. I took a ride in the vehicle and I thought, hey, this is great. This is scary, but it's great. It works. It can drive with 1 camera, not 1,000 LiDARs, not 20 cameras. It can drive with 1 camera. But I know this, but I had a problem. The vehicle didn't know where to go. It was just following a lane. You didn't know where you will end. You couldn't make the vehicle take a left turn or a right turn. It wasn't anyhow controlled by any signal. And I thought to myself, this is something that I can work on. this is I can do something better based on this idea. We invented CARLA. And that's the reason why we invented CARLA, actually. We say, look, we're gonna need a platform so that we can train models and we can evaluate models. So why don't we put together this flexible simulation platform? We're going to focus on autonomous agents. It's going to be open source. It's going to be cool. We're going to have a simple API that we can use because we are researchers and we want something simple. And yeah, maybe other people can use it. Yeah, we'll let them use it. But we are the ones who want to use it. So we created CARLA. And, one of the advantages of CARLA is that it's very easy to use. So here in the screen, I'm just showing like a Jupyter notebook of a tutorial where you can easily spawn vehicles. You can equip those virtual vehicles with any type of sensor you want, any configuration that is useful for you. You can start acquiring data and ground truth, and with that, you can train your models, right? And I'm gonna show you later how actually this is quite valuable. It's not just a toy that is fun to play with. It's actually quite valuable. So here you can see how the data acquisition process goes. So it's very straightforward. And you can get any type of ground truth that you need for your system. So we created CARLA, and then so after visiting these guys in New Jersey, I came back to Barcelona where I was finishing my PhD, and I talked to a young guy called Felipe Codevilla who had just joined the team. I say, hey, Felipe, are you interested about end-to-end driving? He was like, what the hell is end-to-end driving? So, hey, read this paper. Notice that these guys are just like navigating in open loop. They don't know where they're going. How about we actually try to add a signal, a control signal, a very high-level control signal that tells the platform if we want it to go straight, make a left turn, make a right turn, or just do nothing. Just keep doing what you're doing. I say, yeah, why not? Yeah, let's try it. We tried out. We started from the same concepts that we have seen in previous papers, right? In the NVIDIA paper and John LeCun's paper, and say we're gonna have a neural network, but then we're gonna have a module that kind of like does the planning for you. Basically, we're gonna take like a GPS route. And we know that we want to move from point 1 to point B. We're going to transform the GPS route into discrete commands, like go straight, now make a left turn. And basically, that is going to go into the neural network, so that when the neural network sees the option to make a left turn, they're going to make a left turn if you tell them to make a left turn. When they see the option to take a right turn and you tell them to take a right turn, they're going to take that action and say, okay, now, great, how do we do it? And we scratched our head for a little bit, and we came up with a very simple idea. Like, we're going to have like base neural network, but then based on the conditional signal, we're going to index different heads, and each head is going to be specialized on each of these commands. One head is going to be specialized in making left turns, another head is going to be specialized in making right turns, etc. And if we want to increase the vocabulary, I want to have 20 different semantic actions, we can do so easily. And we don't have to retrain everything from scratch. You have new actions, you can just add it, train the head with data for that action, and we're good to go. And another thing that we did here, and this was a great idea from Felipe. So back in the day, the NVIDIA work suffered from a very significant problem. So in imitation learning, when you are using imitation learning as a technique for end-to-end driving, you're typically telling your agent what's the right action to take. But you're never telling your vehicle what's the wrong action to take. Basically, if somehow your agent ends up deviating a little bit from something that has observed, it doesn't know what to do because it has never faced how to recover from wrong actions, from configurations that are ill-posed. So the NVIDIA guys have to engineer complex way to create synthetic images from the real world using multiple cameras to kind of try to tell the vehicle how to recover for ill configuration. Felipe have this idea like, we have a simulator. We can just inject noise and tell the vehicle, come back to the center of the lane, recover. And that will work great. So we didn't need any fancy setup. It's like, do this in simulation and your agent will learn how to recover. You inject some noise and the vehicle needs to recover from this noise. And it worked, and it was perfect. And we published CARLA along with this technique. People like it a lot. We compare different solutions like reinforcement learning and imitation learning, or behavioral conditional imitation learning, which is this technique that I was just presenting, where you can select between the different heads, and a modular approach. And we showed that actually conditional imitation learning worked very well and was superior to all the other techniques at that time. And then after that, I moved to Intel. There was a very smart guy called Jiang Gao from UC Berkeley who came and said, hey, I want to work with you. What shall we do? Let's do something. Why don't we try to bridge the reality gap? Why don't we try that? Like, because when you train in simulation, people feel that it's still complicated to deploy any model that you have trained in simulation in the real world. Can we work on this problem? And we set to do this. So the objective was, we're going to train in CARLA, we're going to deploy in a real car, and we're going to drive. We're going to just drive. We're not going to see any single real image. Berkeley was very kind. They have a vehicle that was equipped with sensor. We say, okay, we're going to ignore all these fancy sensors. We're going to use one camera or a few cameras. We're not going to use LiDAR, anything else. Thank you. And we came up with a simple idea, inspired by one of our colleagues, Matthias Müller, who in the past have worked with RC cars. He noticed that the domain gap is not like equidistant when you move to from real to simulation. The domain gap is shorter than when you move from simulation to the real world. And that gives you an interesting opportunity because you can try to come up with an abstraction. For example, based on a perception stack, you can train, a semantic segmentation model or anything in real-world images, and then have that to be, the input of of your neural network so that that module takes upon the task of creating a common subspace for the real world signal and the synthetic images. So that module basically abstracts away most of the complexity of the synthetic image and the real world image into a common representation, into a common subspace. And based on that, basically, you have defeated the main gap. And now you can train in simulation, and the network is not going to notice if you're running on simulation or in the real world. We did that. We created this simple architecture, with multiple cameras, sort of following up on the previous works. Train on simulation, train on CARLA, create a few things, a few environments, etc., and then deploy in the real world in Berkeley. It worked. And I have 10 minutes, so I have to speed this up a little bit. And it worked. And we say, great. Now we only need better training mechanisms, because our current training mechanisms are kind of like simplistic. We need someone to come up with better training mechanisms so that we can make the most out of the data that we have in simulation. And then enter Brady. So Brady was a very amazing master student who came and said, hey, I have this intuition that, it's hard to train policies, agents end-to-end when you start from images, but inspired by everything that is happening in the world of reinforcement learning, if instead we focus first on learning a simplified representation, very abstract representation, where we for example, represent vehicles as boxes and pedestrians as dots, and we just train an agent with that information, I think that agent is going to be able to generalize better. So our generalization is going to be better. We're going to need less data to be able to perform better in different situations. And after that, we can take that agent that is cheating, basically because it's receiving this special signal that doesn't exist in the real world, and we can have that teacher teach another neural network that can only see sensor images. And because that teacher is going to be able to provide a stronger supervision, we're going to be able to get a better agent that is able to drive from sensor data in a shorter time, needing less data. It worked. Like, it was a good intuition. He was quite brilliant. He made it work. They actually win the CARLA challenge that year. And many people starting to use this technology. So you can see here how this works in CARLA. It was great. It was a brilliant idea. They improve, they reduce the sampling complexity and improve the training protocol quite significantly. And everybody started using this. In fact, like, my PhD advisor had a project with Volkswagen, and Volkswagen came up with this idea, like, oh, there's this region in the Spanish Pyrenees, in the mountains, like this super crazy challenging area, and we want to have a platform that does like robotaxi functions, because there are people living in a small village there, and they're very old, they cannot drive anymore, there's no public transportation, taxis are too scared to go there. Can you do it? In 6 months, using Brady's approach and using CARLA, they were able to train an end-to-end approach and put together a robotaxi that can go through the mountains, Oops, take a look at the video. It was quite impressive. I was very impressed by that. So, a few kilometers here in the mountains. They took CARLA. This is CARLA. We did a digital twin of the environment. They trained in CARLA using the technique proposed by Brady, and they just deploy. This is my PhD advisor, Antonio. Like, he's always super scared. Like, you will never see him like really put his hand very far away. And I understand. You see snow conditions, etc. It was very impressive. It was very impressive to see that these guys with simple technology could put this together. It was amazing. And then a colleague of Brady came over and said, you know what? That's great. I have more ideas about how to improve sampling complexity and how to achieve better generalization. I was like, what do you have in mind? And they say, well, right now telling the agent this action is the best action. How about if we were able to tell the agent this action is a 1, is the best action, this other action would be a 0.9, this other action. What about if we can describe the whole action space? What about we could generate a reward function that is easy to sample from, similar to what happens in reinforcement learning. But I say, well, reinforcement learning is hard, like sample complexity is very high. And he came up with this idea, like, well, if I first train a policy for my agent, the same way we have been training policies in the past, and then I assume that based on the data that we have acquired, the world goes on rails. Basically, I keep propagating this agent forward without considering the interaction of all these other agents with the ego vehicle. I can create a very simple function to sample the world. It's definitely not very realistic because obviously those agents should react to the actions of the ego vehicle, but it could give me enough information so that I can sample these reward functions in runtime very cheaply and come up with a model that basically performs better. I can gain a lot of sample efficiency by being able to, during training, to know that this action is a 1, this action is a 0.9, this action. And again, he was right. And it was a great intuition. And this became the state of the art. And they win the CARLA challenge. And everyone was like, wow, this is amazing. And now he works at Waymo. And then other folks say, okay, yeah, this is all good. But there are situations where we don't have enough context, and we have sensors like LiDAR that are perceiving some signals, and we have sensors like cameras that are perceiving other signals. Like in this case, like, oh, if I'm the ego vehicle, and one of my sensors sees these traffic lights on the right, I only care about those traffic lights in the context of those other vehicles that are going to start crossing. How do I make this association? And some of this information comes from some sensors, some of this information comes from other sensors. How do I do that? And they were quite clever, and they say, how about we do this? We have like a branch, a neural network processing the images, our camera sensing. We have another branch processing the LiDAR, but then we're gonna link them with transformers. And we're gonna get the transformers to learn how to correlate the features. And it worked. And it became the state of the art. And it won the CARLA challenge. And everyone started using it. And then finally, one of the big issues of these technologies, and people were complaining about it, is like, yeah, sure, end-to-end is great, and it kind of works, but you don't know what's going on within those weird black boxes. They could kill you eventually because you don't know if they understand what's happening. And company Wave say, we could work on this. And they say, how about this? We're going to have this object-level simulation platform that is going to create these high-level abstractions, and we're going to use a lot of traffic scenarios, and we're going to convert them into a simplified collection of tokens, like describing vehicle 1 is in this position and this orientation, vehicle 2. And now, with this text description, we're going to ask ChatGPT a bunch of questions, like, what are you doing? What are you going to do? Why are you doing what you're doing? And do you see any dangers? And based on that information, then we're going to fine-tune an LLM to drive, like produce commands, like steer your steering wheel by 25% or by 30%. And we're also going to ask it to explain why it's doing what it's doing. So they used ChatGPT to create this huge database, retrain and fine-tune an element, and boom, it worked. And they used it in production. And it was great. And after that, they decided to come over and win the CARLA challenge this year with a similar architecture called CARLA that basically leverages visual language models to do two things. The generation of the trajectory and the control commands, and a description of what's happening. So similar to the previous approach, but with a slightly different architecture based on VLMs. So before, the previous architecture was fully based on NLMs. In this case, they tried to combine also visual data to make it more robust. It worked very well. So well that they actually took the first position in the challenge this year. And it was one of the best VLM solutions that we have seen so far. Before concluding, I have been asked many times about, well, but how about the domain gap? How do you deal with domain gap? Look, there are many ways to deal with the domain gap. The most basic ways, there are the two main branches, which are like projecting real-world data and synthetic data into a common subspace, and you find how to do that using domain adaptation or any technique, or basically translating like from one domain to another, using automatic image-to-image translation processes, you name it. Something interesting is the approach that Wave used early on, which is we're going to train our models in simulation, okay? And then when we receive real-world data, in order to deploy our model there, we're going to take the real-world data and we're going to transform it into simulated data. We're going to do image-to-image translation. And with that, our vehicle is going to bridge the domain gap. And it worked. So for people thinking, well, how about the domain gap? Well, there are many solutions for the domain gap. Don't be scared of the domain gap. It's 2024. I think we can do it. Thank you.